difference equation where we have it's a first order system with t times a. Let's say if there's a factor a in there. So this is corresponding the resulting design that we can use. So last time we also talked about the frequency response and so on. So we just talked about the frequency response of the system. So conceptually, it should become clearer and more and more clear that this exponential decay function really corresponds to low-pass filtering. High frequency will be rejected, and low frequency would simply be smoothed. I mean, the system performs smoothing. So frequency response, we expect the magnitude response. We expect the magnitude response to be low pass. But we also spend some time to talk about the phase response, right? We also spend actually quite a lot of time to talk about the phase response, and I was trying quite hard to share with you a geometric interpretation. So remember that last lecture we were looking at around the circle. We were having this picture of a particle, sort of, which goes around in the clockwise direction around the center, around the origin, and with a radius of e to the minus alpha t, which is our factor right there. So that was about phase response. For this particular example, we have a geometric interpretation. And in the end, we didn't quite not allow, so in the end, we briefly introduced the group delay. Okay? So turned out that this phase response, if we just, let's say this is phi of omega, okay? So group delay would be defined as minus the negative of the first partial derivative of phi against the frequency. Phase spectrum, you take the first derivative of the phase spectrum against frequency, and you get a delay. So this week we will start from, so that's kind of a recap for last time. And this week, today, we are going to talk about a better way of designing a filter, similarly a low-pass filter. We introduced a better way, and that method is called bilinear transformation. But the idea is pretty similar. Still, we have a kind of an analog system that we think is good. I want to copy that into the digital domain, right? But turned out that the better way, there's a nice systematic way of how to transform an analog filter into a digital filter via this transformation, this bilinear transformation. Bilinear transformation. Okay? Bilinear transformation gives us, let me just write h of s of z, where this s of z, as the notation suggests, 就正如它符号所写的as suggested by the notation, s becomes a function of z. That's what the transformation is about. S is the Laplace S, okay, Laplace S domain, right? E to the minus st. So now, if I invite you to think of S, can we kind of shut the window for briefly? Okay, so S as a function of Z. So there would be a mapping from the S domain, from S, real S, imaginary S, from complex S to complex Z. So that's a transformation that we are talking about, denoted as B, bilinear transformation. So we'll go from S to Z. Therefore, we turn, and by doing this, we turn an analog system function into a digital, discrete time system function. Okay? So that's the idea. So that's a more general idea than simply sampling our impulse response. Okay, and we argue that this is a better way of doing that. Okay, so yeah, let me switch to my personal microphone, which is wearable. Hello. Oh, louder. Okay. All right. So let's come back to the lecture note. So as I was talking about designing a filter, right? We're designing a low-pass filter, and here are some like details I want to point out as a reminder. So last time, oh, this is really loud. Can you control? Is it? Yeah. We can turn down the volume a little. Yeah. Hello. Yeah, that feels better, right? Yeah. Less reverb. All right. Thank you. So last time we pointed out that this difference equation can give us magnitude response, but there's a thing that the magnitude response does not go all the way to 0. Even if when we reach the highest frequency, the Nyquist frequency, the magnitude response does not go to 0. Instead, it goes down to from its gain at DC, which is TA divided by a factor of 1 minus R. It decreases to TA divided by a factor of 1 plus R. Okay, so that gives you a contrast. A contrast between low frequency response, and high frequency response. The window is a low pass filter, by the way, analog filter, acoustic filter. I'm serious about this. It's about some way diffraction through slit, low pass. So we reject the high frequency, okay, by shutting the window. 机会教育。But there's a contrast. I mean, the response drops, from TA divided by this, from 1 over 1 basically the contrast is 1 minus R, 1 divided by that, versus 1 divided by that, okay? R is a positive number, right? So we can kind of give some additional notes here. So here we have a note, an additional note. So if we divide by the low frequency gain and versus high frequency gain, roughly speaking, this quantity now is equal to 1 plus R divided by 1 minus R, because the gain is 1 over that, right? And this provides a contrast. You can think of this as a contrast. Now, 对比, contrast. Think of this as a contrast. Because it makes sense when we design a filter. When we design a filter, we want the filter to perform low-pass filtering, right? So we want to preserve low-pass while preserve low frequency while rejecting high frequency. Therefore, this contrast tells us the ratio. We want it to be high, okay? Just relatively to the low frequency part, we want the high frequency to be as small as possible. So we want to increase the contrast. So we want low frequency to be high and high frequency to be low. So when we divide that, we want this number. We desire to have the higher the better. Okay. We want this quantity to be high, right? And as you notice that this quantity is controlled by R. So when R approaches 1, when R approaches 1, that means we have high contrast, okay? So design principle is probably, so this probably suggests that we want R to be close to 1 so that we have a high contrast between low frequency preservation and high frequency rejection, right? We want this contrast to be good. But yeah, so this is not ideal. I mean, this filter, when we go to the very high, the highest frequency, there's still some residual. High frequency can still pass through the system even though, however small it is, it's not zero, okay? So there might be some way to improve this design, okay? So now we'll talk about that very soon. So keep in mind that this design can be improved because the contrast might not be so good. But then after that, we talk about the phase response. Okay, so let's review this. We talk about phase response by a geometric interpretation, and so we were focusing on this vector, how this vector varies as omega increases. Okay, as omega increases, how the angle of this vector changes. The angle of that, and technically we also need to make it negative. Okay, but so I present a geometric interpretation because this vector, that vector really is shown here as the arrow. So you know the arrow changes direction. This arrow changes direction, and how much of the arrow counting from zero angle, right? It goes like this way, and this angle keeps changing as omega varies. Yeah. So that's our phase response essentially, okay, with a negative sign. So it's just geometrically, it should be pretty clear. In the textbook, somebody asked me about if we can express it. Does this angle have a closed form expression? And the answer, of course, is yes. Okay, this angle equivalently, if you wish, you can express it. You can express it as negative of arctangent of what? Imaginary part divided by real part. Okay, imaginary part of this complex number divided by real part of this complex number. So let's be careful. The real part should be, if I do it correctly, I hope I'm being correct. 1 plus r cosine omega appears to me like that's the real part. And the imaginary part seems to be sine r sine omega. And put the arctangent, that's an angle, and with a negative sign. So with this expression, you may as well make a MATLAB plot, for example. Okay, so you know how to express it. In closed form. Okay. And with that, then so either by geometric interpretation or by the precise plotting, you should be able to conclude that the phase response goes this way. Okay, it increases till it reaches at a certain frequency. It reaches a maximum angle, right? Reaches the maximum angle, and then it drops back again. Yeah, it drops back to Nyquist when we hit Nyquist frequency. The vector is flat again, so the angle is 0. Do you see what I mean? Yeah, there is a tilting, and then it goes back. Yeah, and there is a particular frequency at which the phase reaches maximum. All right. So then further, we talked about group delay. Okay, the group delay's definition is the first derivative of the phase response against frequency omega. Okay, so we can just I argue that this is a latency or delay, and again there's a negative sign. And let me tell you a few things. First of all, I think tomorrow we have a follow-up discussion, right? And so did I list the group delay as one of the problems? I forgot. Did I? I didn't? No, so in your homework 4. Okay. Yeah. In your homework 4, I will design, you will learn more about group delay. But at the time, I can share with you that there's a problem in the textbook. Okay. So I'll assign that problem in the textbook, which explains why, what does it mean for a system to have a group delay. Delay of what? Okay. For delay of a signal. Okay. And this group delay, in general, you can imagine it will be a function of frequency. So if we just plot the group delay, for example, if we just attempt to plot this is pretty, oh, yeah. So if we just plot the group delay, let's say tau g, and in general, it's going to be a function of frequency. Okay, so this is pi. Yeah. So tau g. So actually, let me make it dashed line. So we should be looking at the black, not the purple. Yeah. So with the negative sign now, tau g, now the phase response really is below. Below, right there. Here is our phase response. Okay. It's always in this case, it's always negative with reaching the maximally negative point at the frequency right there. So just you can plot the group delay now by trying to figure out the slope, right? The slope. It's really that easy, okay? So the group delay here, it turns out that the slope is largest right at DC. So DC will have the highest group delay because the slope is maximally negative. 最负. Is it okay? Yeah, because the slope with a negative sign is the group delay. So note that here, right at DC, that's where we hit the maximally negative slope. Right at DC. So right at DC, we have the longest group delay. But then the group delay goes to 0. Yeah. It just decreases to 0 at when the phase reaches a local extremum, 有一个极值的地方啊。But if we go further, the group delay can also be negative. If we go further, the group delay can also be negative, and then that's as a matter of fact. The group delay plot may look like that. Okay. So seriously, that's how we perform partial derivative of the phase against frequency. Just check the slope. But what's the meaning of group delay? When the signal goes through the system, is processed by the system. When the signal is processed by this system, what does it mean? What does group delay mean? So we need to consider group delay should be understood by creating a context. Okay, creating a context. What context? 要一个情境, create a scenario. Okay, so let's assume the scenario is that we have a signal that is narrow banded. Let's assume that our signal is narrow band. Assume our signal is narrow band. So that means that our signal, when we consider its spectrum, when you consider spectrum, maybe most of the content is around a center frequency omega 0. The energy, the power spectral density is around omega 0 with a kind of bandwidth, with a narrow bandwidth. With a narrow bandwidth when compared to omega 0. So when we go back to, so there's a duality in signal processing, meaning that when we have narrow bandwidth, that means we need the signal in time should be long, and so on. So it means that we may have a long signal, which which has an envelope, and inside which the signal may have a carrier. Okay, for example, this can happen in communication, right? When the carrier delivers message which is encoded by an envelope. We talk about amplitude modulation, right? Yeah. Yeah. So, for example, if our signal seems to have an envelope, 一个包络线 envelope 啊，信封封包啊 ，which modulates the carrier and the carrier frequency might be just omega 0. Okay, so that's a context. That's a scenario when we really have a narrow band signal. Okay, with small bandwidth right here compared to its carrier frequency. Then group delay gives us a prediction, a sort of a precise way to evaluate what time would the system with the signal appear in the output. Okay, let me say that again. Yeah. Group delay gives us a precise way to evaluate what time will we see the signal in the output. We know the input is right like that, right? Input is right like that, but how about the output? Okay, suppose that in the output, sure, yeah, the envelope may look different shape, but group delay tells us a time shift. Okay, between the time the signal appears in the input and the time the signal appears at the output. So this difference is, roughly speaking, is what tau g is trying to tell us. Group delay tells us this delay, but this is not being precise enough. Okay, this description is not that precise. So to be more precise, precisely speaking, tau g, we need to define what do we mean for a signal to occur at some time. Do we mean this time when we first see the signal, or what? Okay, so strictly speaking, tau g really, we need to define the signal tx and signal time tx and time ty as the centroid time. 直心的时间 centroid time. Okay, so we need to, when we define tx, the centroid time when the signal occurs in the input, that can be defined as an expected value, 期望值 an expected value, so it's weighted by the amplitude square. So on top, we need to sum time n xn square. That's what we mean to calculate the centroid, 直心的时间 the centroid time. Yeah, in terms of an expected value. Is that clear? Think about xn. Wait, I'm missing a summation n right here. Yeah, sorry about that. Yeah. And similarly, we define the centroid time for the output signal as the expected value according to its energy. Okay, so we define kind of the centroid time for input and output. Okay, and then we can show there's a way to show that tau g is approximately ty minus tx. Yeah, simply enough. Yeah, if the spectrum is narrow enough. Okay, tau g at omega 0 at the center frequency. Yeah, tau g itself is a function of omega. But when we evaluate group delay at the center frequency of this narrow band signal, when we evaluate that gives us a good estimation, a precise estimation of the delay time, ty minus tx, in terms of a centroid, weighted by the signal energy. Okay, so that's why group delay is also called energy delay. It's also called energy delay for this very reason. So therefore, it's also called energy delay. Yeah. So I'll leave the details to the homework. Okay. So there is an exercise in the textbook. I will assign that as part of homework number 4. So wait until then. But group delay really has a meaning. It really has a meaning of how the energy is going to be late when the signal goes through, when a narrowband signal at that frequency goes through the system. Okay, so that's why group delay can be a function of frequency, as you can imagine. All right. So any questions so far? Yes? All right. Okay, so now I think we are ready to enter the next lecture. Okay, our next lecture is an improved design. Okay, and I've named the lecture as IR design, IR filter design, infinite impulse response. Okay, so we'll have the resulting outcome is again a difference equation with feedback coefficients. Okay, IR system design through bilinear transformation. Okay, and I'll argue that I promise you that this should be a more sophisticated, 比较老练的, more sophisticated and more a better way of designing an IR filter. Okay, but the take-home message, right? So I want you to be sure that the idea of designing this IR filter by this method, again, similarly, we will borrow from analog. We borrow from analog. Okay? Yeah. That's still the idea. But the way we borrow it is quite different. We borrow it directly from the Laplace domain. Okay? Instead of working in the time domain, we borrow the system function directly from the Laplace domain. Okay? And how do we do that? So here is an example. Okay? This example actually gives you, just surprisingly, it gives you a low-pass filter which have a lot of nice properties. Let me slowly explain. So the analog system right here is characterized by its system function. Okay? Suppose that the system function here is expressed as like that, where C denotes continuous. This is a continuous time function characterized by its system function in S. But now this system function can be factorized. We assume that it can be factorized into the product of 8 terms like that. S minus Sk, where K are the location, Sk are the location of the poles. Okay? And so this is a classic example. Okay? In this classic example, that we are showing the location of the 8 poles. And they are all gonna be on a circle. And note that this is a circle in the S domain, not Z domain yet. Okay? Not Z domain. But it turns out that for this very filter, the poles are all located on a circle in the S domain. And they all occur on the right-hand side of the imaginary axis, right? No, not right hand, left-hand side, 左边, 左边, left-hand side. And we know that for those of you that are familiar with some systems, for analog system to be stable, all the poles need to be on the left-hand side. Okay? Otherwise, when we perform inverse Laplace transform causally, we have an exponentially growing term. Okay? So keep that in mind. So this system, we can check, yeah, sure, it's good to know that all the poles are on the left-hand side of the imaginary axis. But it just turns out that they also occur on the same circle. And we are not going to show it right today, but it turns out that when we arrange the poles like cutting pizza, okay, into equal pieces, I'm not doing a very good job. Imagine cutting pizza at perfect angle, okay? Turns out that if you do this arrangement, then surprisingly, the magnitude response is a monotonic function of frequency. And this is a low-pass filter, okay? Yeah. So the surprising thing is that we have a monotonic decreasing low-pass filter, low-pass response. And in fact, when we put the pole location, when we perfectly adjust the pole location like cutting pizza, okay, this filter has a name. It's called what? The name escapes me. What is the name of this filter? It's a famous one. It's not Chebyshev, but what's the name? Butterworth, okay, Butterworth, yeah. This filter has a name. It's so classic that it has a name that people in this field knows about, okay? You need to know that. You also need to know that. This filter is so classic, we refer it as the discoverer of the filter named it after his own name, Butterworth filter. Yeah. Probably the name of an engineer. Butterworth filter. Okay, and the Butterworth filter has a very nice, simple expression of the magnitude response, which I'm going to show you in a moment. Okay, the magnitude response, in fact, has a simple closed form of constant divided by 1 plus omega divided by omega c, a cutoff frequency to the 2nth power. Yeah. Okay, so let's stop for a moment. Okay, let's stop for a moment. Okay, I want you to look at this really nice response. Okay, really nice response. And here we have a few parameters. Okay, so just even forget about digital design. Let's not worry about digital design yet and focus on this analog response. Okay, this magnitude response is parameterized by two things. We have the parameter of omega c and the parameter of n, right? And n is simply how many poles we have. Yeah. N is the number of poles, or another piece of pizza we are cutting, okay, if you will. Number of poles around that circle. And omega c being the cutoff frequency is simply the radius. A radius of this very circle that occurs in the Laplace domain, and we are placing the poles on the circle of this radius. And this radius turns out that it gives us it is exactly the cutoff frequency. Why? It is exactly cutoff frequency in terms that when omega equals to omega c. When omega equals to omega c, the gain is cut in half. Gain square is cut in half. Okay? So gain itself, I'm not doing a very good, let me just put the square right here. So the square of our gain now is cut to 1/2 of the DC gain. Okay? If the DC gain is 1, then at this corner frequency, this parameter, at that very frequency, the gain is cut in half, right? Because 1 plus 1 is 2. Simply like that. So this is a corner of the cutoff frequency, okay? Where the gain drops from 1 to 1/2. Okay, so omega c is meaningful. And how about n? N occurs right here. Okay, so n tells us n is an order. Okay, n turns out to be the order. This is n. in this very example, in this particular example, we have 8 poles, so n is 8. Okay, so n is the order of the filter, but it gives us a control of how fast we want the response to make a transition from pass band to stop band. Let me say that again. So n controls how fast we want the response to make a transition, 过渡, to make a transition from low pass region, from pass band to stop band. Okay, so what does that mean? So we may have, so depending on n, we may have a slow transition like that. That's a slow transition. And to make a faster transition, we might intend to obtain a design like that, right? So as n increases, pass band become more pass, and stop band become more stop. That's not English, but I hope this is clear, okay? When n increases, we make a faster transition from the pass band. This is our pass band, right? We make a faster transition from pass band to stop band. Ideally, we want pass band to all have gain 1 and stop band to all have gain 0. But we know that you can never, engineering-wise, that can never be achieved, right? So, but now it's nice that in this Butterworth filter, we have the order of the filter is going to control how fast we can make the transition. Okay? When we need faster transition, usually that's desired. Usually we desire faster transition to best preserve the pass band while best rejecting the stop band. Okay? We want to completely reject the stop band while completely preserving the pass band with equal gain. Right? That's an ideal filter. Okay? So n is a nice thing to know. So depending on how 你的期望有多好, depending on how fast you want the transition to be, you need to select the order of the filter. Okay, so that's kind of the motivation. The message here really, what do we learn so far? Analog is cool. Analog, if you're interested in analog, there are a lot of things to explore. Yeah, a lot of like a background knowledge. Yeah. So this is just one little small cool thing right here. Butterworth filter, and there, if you just design your system to locate your poles right on the circle, on the left-hand side of the circle, then chances are you may be able to create a filter. You may be able to create a magnitude response which not only decreases monotonically, but also we can control the transition. Control transition and freely select your cutoff frequency, make it monotonous, and you can control it. There's a control. It's a very nice design, classic design. Okay, so hopefully this motivates us that maybe indeed, when we go from analog to digital, we want to still be able to borrow previous knowledge that people have found out in the past. We want to borrow the knowledge and make our and migrate to the digital world. Okay. All right. So that's a bit of a background. Okay. And let's now officially introduce what is bilinear transformation. Okay. Bilinear transformation is simply defined in this equation. Fairly easy. Okay. Bilinear transformation is a function S. Is S as a function of Z. S as a function of Z. And there's also a free parameter right here, where TD has a unit of second. TD really is the time, as you might have guessed out. Okay, Td is some sort of a parameter which has a unit of time. Because it has a unit the same dimension of time, but otherwise, what's more important is inside here. Okay, inside here we have 1 minus the inverse divided by 1 minus the 1 plus the inverse. Okay, so essentially s equals to this function with a scaling factor. Okay, there's a scaling factor, and so that's simply a definition, and we will study its properties very soon. But let me now mention that now we claim that we can design a filter by borrowing an analog system function like that, and we claim that this already is our design. Okay, starting with anything like that. Okay, this is a system function in continuous time, right? Starting with that, and then replace s with s of z right here. So seriously, we are doing this. HC, we are going to evaluate HC at 2 divided by Td, the parameter, times 1 minus the inverse divided by 1 plus the inverse. Seriously speaking, make this substitution, and then the result now becomes a function of z. It's pretty simple, okay? Hopefully this is pretty simple. Make this substitution whenever you see s, replace it by s of z. This is s of z, right? And then the result now, of course, we might need to organize the terms algebraically. 代数上面要做一些整理啊。We need to organize different terms, but in the end, we can all agree that this becomes, now it suddenly becomes a function of z, and we claim that this is a design. Okay, this is a design in terms that most likely you see hz can be expressed further as bz divided by az, and we know how to change that into a difference equation. So the rest just follows. The rest just follows, but the beginning step is important. Beginning step is to start from analog system, make the substitution, and make the bilinear transform substitution, and then the result becomes a system function in the z domain. Okay? And we claim that this is a design. Okay? We claim that this is a design. So let me mention that because some of you have been asking, where do we find the content of the lectures in the textbook, right? So, but for today, thanks for the reminder. Today, I remember to share with you that this content can be found right here in the textbook. Okay, it's in chapter 7, and please check it out when you go home, right? But anyway, so this is a simple enough a definition that's simple enough. Now, next, let's see an example. Okay, see how we borrow an analog system and make it digital, and call it a design, right? So just now to move on, let's still come back to this same example. Let's come back to this same example, same as last time, okay? Same as last time, so remember that we were trying to emulate a circuit. We emulate a circuit with, not in series, but in parallel. So we emulate the system of delivering a current to the parallel connection of a resistor and a capacitor, right? And we were, the output is the voltage right there, okay? Yeah. So that's our system, and we know that with some simple algebra, we have the following transfer function or system function right there. Same example, right? Same example, and suppose that we know that just further we have this the system function can be expressed as like that. Now to move on from S domain to the frequency response, what do? We evaluate the transfer function on the imaginary axis, right? For analog system, for an analog linear system, when we need to evaluate, we need to figure out the frequency response. What we do is to evaluate the transfer function on along the imaginary axis. Just simply replace S with J big omega. That gives us the frequency response. Okay, that gives us the frequency response. And from last time, or from our previous discussion, or just simply by looking at this expression, you can convince yourself that indeed, at DC, we have a unit gain. Okay? At DC, we have unit gain, while you know what? I think I'm not being 100% correct. 我的单位有点问题啊。So yeah, it now appears to me that now this gain has no unit. It's not ohm, 并不是欧姆或者什么。But in fact, if we divided V by I, shouldn't we get a resistance? So there might be a missing factor of 1 over R somewhere. Okay, please don't worry too much about that, because I want to organize my frequency response in that so that it has a unit gain at DC. Okay, it has unit gain at DC, and then as frequency increases, we know that the magnitude response is going to be decreasing. Okay. Decreasing, and when omega approaches infinity, the gain becomes 0. Approaches 0. That's a property of this transfer function. Okay, of this transfer function. Okay, so suppose that similar. Actually, I think this filter, right, just to connect to Butterworth filter. This is actually the first order Butterworth filter. I think it is. Just by chance, it turns out that this is a first order Butterworth filter with a color frequency. With a color frequency at 1 over RC right here, RC being shows up right there, and also the magnitude response is a monotonic function of the frequency. Okay, So let's take a break of 10 minutes, and when we come back, we will examine what if we plug in, we make apply the bilinear transformation to migrate from analog to digital. Okay, let's take a break. 哦，
就还要写
好，我可能写了1/2。
所以
对对
就是假设这个是一，然后
对，
小的问题。
在那个这个频率的地方，它会降到1/2这样。哎，它的啊，
那那个什么，就是这个，就是什么？
对
刚刚有前面写什么 II 的这种，
，IR 是哪3个字是？
对吧？
啊，好，等一下我觉得我应该要跟大家讲清楚，第一个 I 是 infinite impulse response，infinite impulse response，就是算出来的东西会是有 pole 的系统，那会有这些 feedback 的 coefficients，然后会是 IIR，就是它的 impulse response 在 discrete time 的时候，它会是就是它并不是它的那个长度是无穷长啊。
这两个就是你刚刚一开始来讲的时候，我其实没有很懂，就是有些人是写什么，是因为这个是 negative response 嘛，这个是 base response，
对。
为什么后面写是什么 geometry？
哦，对我是讲说上次上课的时候，我们花了很多时间讨论那个箭头，还有那就是一个几何的解释，对对
然后对应就是他现在是找到哪个？
对，呀，哎，
是用几何的方式去
可以做图了，对，可以做图，哎，
对，
好，还有呢？
我就是前面，这个我就是他这边就是 narrow band，
对，
之前讲那个 band limit 其实是一样概念。
我觉得不太一样哦，这是非常好的问题，因为 band limit 那时候整个情境，我们是在解释说continuous time，然后要去做 sample 的时候。
它那个种就是它那个傅里叶转换结果会是一个就是三角形。
对，是有限的，但是我们现在比较强调是那个是有限，但是可能它可以很宽呐、可能还是满满的，从 DC 到高频都有啊，只要是有限的，那叫做 band limited。但我现在讲 narrow band，意思是说那个频宽就相对于它的中心频率来讲是蛮窄的。
哦，所以那个 band limit 只是它是有限，但是它可以很宽。
它也可以很宽。
如果是那个 narrow band 的话，就是它离它那个中心那个频率是很近。
对，就是说频率是集中在中心频率附近的。
频宽很窄。
对，频率是集中在中心频率附近，哎，这个意思。
你这边就是一开始是第一的时候，为什么就是这边你是写就是约等于，而不是写等于？
嗯。
可是这个旁边很重要。
我看一下啊。
我说这不是 LTI system 嘛，所以它那个它不是就直接等于就好了，应该没有重要。
对我可能这样写的，这样写不好，我这样写不好，我应该写说我们要那个 LTI system such that 它的行为很像是这个行为啊，因为 LTI system 它 difference equation 它永远不会直接 work 在 continuous time，哎，所以我这边可能这样子表达不够清楚，应该说只是用设计某一个 difference equation， 让它的行为，让它所展现出来 I/O 的关系会很类似于这样的关系。
所以就是它在就是那个 discrete time 的时候会等于，但问题是它在 continue 的时候，它只是很近似这个结果，但是不是这样。
就是说，即使你这样讲也很好，就是说我们如果是现在 discrete time 会很近似的话，但是永远不会是等号啊。即使把它到了 discrete time 以后，因为还是有一些的差距啊。毕竟长条，比方说在做 convolution 的时候，它那个长条图的总面积一定不会恰恰等于曲线下的总面积啊，所以我们只能写近似而已啊。即使再把它转回 analog， 也只是近似。我们看看，这有个减号，这边可能是减号，对 ，you might be right，you must be right， 对，应该是减号，对，好，谢谢，好，我来做一个修正啊。好，谢谢啊。对，因为有一个小题好像蛮明显，很简单那样的。
好，那所以就是那小题跟
就是合并，对，呀。 好像还好啊，比较不能接受这噪音了，这样子是真不是办法，这时候在施工。啊，哎，没关系，就是还在可以 OK 的范围了啊。所以先前的 lecture 都有上传到 OK 好，有人观看的次数多吗？还正常就是，那就好，好啊。Okay, so yeah. Can we start again? Yeah. Okay, so first of all, let me make a correction. I think one of you to show up to come to me, and point out that I made a mistake right here. Okay, I made a mistake right here. Please make a correction. It should be minus, not plus. Okay, so if you will. Yeah. Thank you for for double checking. Yeah. So there's a mistake I made right here. Yeah. So please also make the correction on your notes. But otherwise, yeah, so we have introduced the bilinear transformation, and now we are about to use it on our previous prototypes system. OK， 想成一个圆形好了。OK， 圆形知道吗 ？Prototype 啊。So analog is a prototype. Yeah. So let me even put it here. Even better. The idea of designing an IR filter is to borrow from an analog prototype. Even more beautiful. Okay? You sound professional when using big words. 从类比的原型来做这个，来获得启发啊。We are inspired by analog prototype. And just also to make sure that we all know the terminology. IIR stands for infinite impulse response. Now, in contrast, later we will talk about FIR. That's IIR. And when the impulse, that means that this system is going to have an impulse response that lasts forever. Okay, that's lasting, that never goes to zero. Yeah. Or equivalently, the corresponding difference equation will have feedback terms, so that we keep producing. Yeah, the system's response to delta function will just be sustaining till indefinitely 无穷的展延下去 It will be extended or sustained indefinitely. Infinite impulse response. And here we are indeed designing systems with pulse. All right, so by borrowing from, so we are about to talk about borrowing from this very analog prototype. which resembles the characteristics of this circuit. And we know that it's a low pass. Turns out that the analog magnitude response monotonically decreases, and it turns out to be the same. It's a first-order Butterworth filter. With a corner frequency at 1 over RC, where the gain, if you will, the gain drops to 1 over square root of 2. And you can call the frequency below that the pass band, above that the stop band, okay, if you will. So this is a low-pass analog prototype that we want to borrow, but the way we borrow it is pretty simple. Now we apply bilinear transformation, okay? Now we just apply bilinear transformation by replacing S with this expression. Wherever we see S, okay, we are going to evaluate the transfer function by replacing S with 2 divided by parameter TD times 1 minus the inverse divided by 1 plus the inverse. This is how we make the replacement. 把它带入进去. So the rest is just pretty straightforward. Just 剩下就是 details. The rest are just details. So to complete the steps, now replacing S with this expression with bilinear transformation. This is where S occurs in the system function, right? So we replace S with exactly this. Is that clear? But now the system function is desirable. It's desirable that we kind of organize our expression a little bit so that at the bottom on top we have 2 polynomials, right? And we can do that by moving this term 1 plus z inverse to the top, right? So I mean just detail, right? Moving this term to the top. So after we do that, then now below we have A of z, and above we have B of z. That's what we mean, designing a digital system. So that's what we mean. Okay, that's what we mean. So now we have BZ divided by AZ, then we can easily just change that back to a difference equation. Okay, it should be pretty straightforward. No, not differential, difference. We can change that into a different equation, and you can implement it. You can implement it in your computer, in your Arduino, in your whatever device, okay? Whatever processor. Right. But now, next, let's contemplate the result. We promise you, I promise you that this is a design, right? But what do we get? What's going on right here? What's this system's frequency response? Is it really going to be a low pass? We are designing a low pass filter by borrowing an analog low pass, right? But is the result, if I ask you, now the resulting system has this h of z, is it really a low pass? How can you tell? Or even, is the system still stable? This is a kind of 有点抽象，对不对？ kind of abstract to think about transforming from S to Z. So the result is it gonna give us a stable system. Okay, so maybe let's check of course I've answered to you that it's rather actually this is quite straightforward. The corresponding difference equation we can also show it. Okay, so which one do we want to answer first? 1, 2, or 3? Make a suggestion. 想要先讨论1、2还是3？ Which one should we discuss right now? 赞成1举手。1，好，2举手。3，好，那就1。Zero and pole location, okay? The pole location, this is also just detail. So the pole, there is 1 pole and 1 0, right? So the pole is at, just be careful, 1 minus 2RC divided by TD. That's at the bottom, and on top, what do we have? It seems that, oh, it's 1 plus. It seems that we have a pole right here. This is our pole location, okay, at z equals to that. Am I correct? 好像是啦 something like that. You know what I mean, right? Seriously, just find a pole location, right? And so that's that. How about the 0? Can anybody tell me where's the 0? Where's the 0? I promise I won't give extra credit on Wednesday. 可以吗？保证不加分。Where's the 0? At what? Where? At z equals to where? -1, right? 负1. Oh. So turns out that we have a 0 at z equals to -1, and which is always true. This is actually pretty general, okay? This is quite general, by the way. Bilinear transformation creates zeros, and sometimes multiple zeros, all at z equal to -1. And what does that imply? Anybody? When we have a 0 at -1, what does that tell you? What does that tell us about the frequency response? -1 是在圆 is on the unit circle, right? At which frequency? -1 is at frequency of pi, right? That's a Nyquist frequency. So having a 0 at the Nyquist frequency, that means equivalently saying the gain is 0, right? 0 is 0, right? That's what 0 means. 0 gain. That means the Nyquist frequency is going to be completely, it will completely vanish. 它完全被消掉 And is that desired in our case? We're designing a low pass, right? So we're designing a low pass, and now bilinear transformation seems to guarantee that we get 0 gain at Nyquist. That's a good property. Okay? It turns out that this is quite general. Okay? When we design a low pass by bilinear transformation, 0 is guaranteed to be located right there at z equals to -1. Okay? This is actually general property. This is a general property. Let me put an exclamation mark because we are happy at this moment. Okay, this is a good design. If what you want is low pass. Okay. Okay. So now we have checked the 0 and pole location. How about stability? Is this system stable? Then we need to check whether the pole is what? Inside the unit circle. Right? We need to check whether the pole is inside the unit circle. And does it appear that, so equally, if this pole is ZP, we need to check whether ZP is inside the unit circle. That's a question to ask. And it appears to me that, yeah, ZP, that indeed this system is stable. Okay? Yeah, you need to check that. And finally, let's work on the corresponding difference equation. Okay, the corresponding difference equation now, we have 1 plus 2RC divided by TD times YN plus 1 minus 2RC divided by TD Y of n minus 1 equals to xn plus xn minus 1. That's just directly by inverse z transform, and noticing that z 负一次方 corresponds to a one sample delay, right? So it should be pretty straightforward that we have this difference equation. But this difference equation, as I mentioned, we want the leading coefficient to be 1. Okay, I will not say this is wrong. This is, of course, correct. Okay? This is, of course, correct. But better, if you want the implementation, it's better to write it this way. Yn equals to 1 plus 2RC divided by TD. At the bottom and on top, we have that divided by TD. Yn minus 1, there's a negative sign right here. Okay? Move it to the right-hand side. Okay? Plus, there is a factor now right here, xn plus xn minus 1. So you can organize the terms in a more tidy manner, 把它整理得更好一点啊。But this is how we obtain a difference equation from our design so that we can implement it. We can run it in real time. Seriously, we can run this system in real time. So far, so good? Everything looks fine for now? Is everything look fine? Does everything look fine for now? Now, finally, there's number 4. Do we really have a low-pass design? So far, we've found out that, hey, cool, we have 0 gain at Nyquist frequency, okay? We have 0 gain at Nyquist frequency, but how about other frequencies? How about other frequencies? So, in doing that, we have to substitute z by evaluate the z transform, the system function on the unit circle. We know the system is stable, right? So we can evaluate the frequency response on the unit circle by, wherever we see z, replace it by e to the j omega. So I need to refer to my what's on top, whatever on top right here. So I'm going to copy it. I'm going to copy this and move it right here. Paste. Oh. Bad. Please, let me redo this. Oh, that's bad. And, anyway, stupid. 重来一次. I'm going to copy this. Copy. And I'm going to put it right here as a reference, right? We need to evaluate it with z equals to e to j omega, okay? Simple enough, right? Okay, that's what we will do. If you are required to, do this in computer, that's what you will do. But now, is this can anybody easily tell me whether this is a low-pass system? Right? Can anybody easily tell me that this is a low-pass or not? Does the frequency response even decrease monotonically? When we further complicate the matter, right? We evaluate the magnitude by putting absolute value, right? Any suggestion? Okay? 有学过不要破梗啊。有时候 who knows? 有的时候有学过吗? Has anybody ever learned bilinear transformation? Okay, yeah, good. Yeah, that's why you want to come here. Okay, yeah. So you see that so far we have told you operationally, 操作上啊, operationally how we really apply the suggestion. I suggest that's the design, right? And you can operationally 操作上面, you can manage to make that replacement of S equals to 2 divided by TD1, something like that, S equals to S of Z, and plug that into, replace S with that, then suddenly you get a difference equation, right? After a few steps. But even to talk about frequency response, we need some extra knowledge. We need to know more about the essence, what bilinear transformation really is about. Okay? So in the next few minutes, maybe next half an hour, next 30 minutes or so, we need to really talk about bilinear transformation. Otherwise, we will pretty much get stuck here. Yeah, because this even for a simple system, the expression looks scary. This expression looks a bit scary. Okay, so we need to approach this by some other angle, from another angle. Okay, 换一个角度来看啊。So next, we need to talk. We need to talk about properties. Properties of this bilinear transformation given by this expression. Still, this is our bilinear transformation, and let's talk about its property. Okay, so I'm going to show you a few important properties. Actually, just I think just two properties. Okay, first property is that S of z is a one-to-one mapping. So I didn't even write it down. So S of z, actually the zeroth property is that S of z is a one-to-one mapping, basically. One-to-one mapping, so it's invertible. Okay, you can express S in terms of z as a function of z, or you can express z in terms of the inverse function, inverse bilinear transformation. So it goes in between two domains. Okay, so first observation you should know is that you can also write z in terms of S. It's a one-to-one mapping. Is that clear? Yeah. Is that clear that here we have, if S as a function of z is that, then z can be written as a function of S. Okay, it's, you can derive that. It's just detail. Take a look. And z as a function of S is now a mapping from S to Z, okay, mapping from S to Z. And it is an analytic mapping, analytic function, meaning that you can talk about dz ds. Yeah, that means we can talk about dz ds. dz ds. Okay? In terms of a Cauchy-Riemann relation. Cauchy-Riemann 方程式 in complex analysis. So Z of S is analytic, it's differentiable, except that it has a pole. 在复变叫做 pole 吗? I forgot. Residue theorem and stuff like that. Singularity. Singularity. It has a singularity. It's analytic except at its singularity, which is where the denominator becomes zero. Okay. Singularity. 有个基点在那边起点 singularity. Except at this singular point. So later, I'm not sure if I'm going to introduce this or not, but it's kind of good to know that analytic function as a mapping from one complex domain to as a complex valued function defined on the complex plane. This mapping preserves, we say this is a conformal mapping. It preserves angle. Okay? Conformal mapping. Maybe I can put it down here. Conformal mapping. Some background knowledge discussion. So now we have the S domain. This is S domain. And we define Z equals to 1减掉2分之 TD 1减掉2分之 TD 看不懂 S 1 just 1 plus TD divided by 2S. Okay, this is a mapping from S to Z. two-dimensional to two dimensions, okay? So any analytic function, when you make the transformation, it preserves angle in terms of that if you create a map from one point to a point, z of s. Let's say this is s0, and this is z of that. Yeah. So the angle, so if you consider kind of a path, two paths, which goes through the point right here with an angle of theta, okay? That angle, if you map the path locally, even though the direction might change, the angle is preserved. Yeah. And this property is called conformal mapping. 保角变换啊。In Chinese, it's called 保角变换, conformal mapping. So there are a lot of background knowledge to understand if you're interested. Okay, so but seriously, I want to emphasize this S of z really maps from a two-dimensional S plane to a two-dimensional Z plane. Complete value defined, and the domain of definition is also complex, okay, on the complex plane. Yeah, so that's some kind of background knowledge to see the transformation as really a conformal mapping, okay? So now it turns out that it's important to know that the imaginary axis on the S-plane is mapped to the unit circle in Z. Okay, yeah. So let's check that first, shall we? Yeah, we can check that. We can check that. So that means for any point S on its imaginary axis, for any point, if S, in other words, if S is on the imaginary axis, then how about Z? When it goes to the Z domain, where does the path become? What kind of path does it become? It becomes a unit circle. Okay, I will show that quickly. We can show that quickly. So if S is j omega, then Z of S is 1 plus Td divided by 2 times j omega divided by 1 minus Td divided by 2 times j omega, right? Yeah. So Z of S, if you consider its radius, now can we all see that the radius is 1? The radius is 1. This radius, when we write it down, is 1. Right? Right. The radius is 1. Why? Because this is simply a complex number divided by its complex conjugate. No, complex number and its complex conjugate are equal length, right? They have equal length. Therefore, when we make division, the result is 1. Okay? So simply, we have shown that if S is on the imaginary axis, after inverse bilinear transformation, it maps to the unit circle, or conversely, okay? You can say that the unit circle, a point on the unit circle in the Z plane, maps to the imaginary axis in the Laplace S domain, one way or the other, right? It's a bidirectional mapping, okay, one-to-one mapping. But more interestingly, turns out that we also know that the angle, we care about the angle, the phase, the angle of Z. Because of the angle, if Z is 1, then we can say Z is e to the j omega, where omega really is the digital frequency, represents the digital frequency after we migrate to digital world, right? So consider the angle, the phase of z. It's pretty important to consider phase of z because it gives you the digital frequency, okay? So let's work on it. Let's work on it. So the angle of z now, what is it? What is it? Should be the angle of 1 plus Td divided by 2j omega minus the angle of 1 minus 2Td divided by 2j omega. Okay? Yeah. So just to focus on this term first, right? Inside, the real part is 1, the imaginary part is Td divided by 2 times omega. Therefore, here we have, just to write it further, develop this further, this is arctangent of Td divided by 2 times omega. Okay? And similarly, we have minus the negative of arctangent, same thing. So okay 吧？这速度啊 ，Yeah. Are you with everybody with me so far? Yeah. Everybody with me so far. So I'm going to just be lazy. Just erase this, and it turns out that there's a factor of 2 in front. Okay. 这不是 z. This is 2, not z. Okay. Let me make it better. This is 2. Okay. Yeah. So that describes a mapping from the imaginary axis to the unit circle. It gives us a relation between small omega and big omega particularly. And this is wonderful. It's very good to know this. It's important to know this. Okay, let's contemplate on this result. So what is going on right here? What's going on right here is that we have a mapping from the imaginary axis to the unit circle, right here, okay? And there's an explicit relation between this j omega, the big omega right here, and small omega, which is the angle right here. And the relation is given to you as 2 times arctangent of that. Yeah. So what's going on? So personally, I find it convenient to rewrite this as 2 times arctangent of omega divided by 2 divided by the factor of 2 divided by Td. Okay? Same thing. Then we can study this. Okay? So you can imagine, again, this is I'm going to share with you a geometric interpretation. Okay? If j omega gives you a point along the imaginary axis, right? So imagine that we have a point right here, and we connect from this point of negative 2 divided by Td. We connect a vector like that, right? So in this case, theta is arctangent of Td divided by 2 times big omega, right? That's our angle. So now can we agree that as omega increases, can you all imagine that as omega increases, as omega increases, this theta, does it also increases monotonically? As omega increases, the theta increase monotonically. Okay? It increases monotonically when we increase omega. When we further increase omega right here, theta increase monotonically, right? And when we further increase omega here, I'm being exaggerating. When we further increase omega right here, and connect all the way, theta approaches 90 度. Theta approaches, just a limit omega approaches infinity, theta of omega is pi divided by 2. Okay? Yeah. So in this way, we map the imaginary axis to the unit circle in the monotonic way. Okay? In monotonic way, in that when we increase omega, theta always increases. But we are wrapping the entire imaginary axis to the half a circle. Okay? There's a factor for 2, so omega, theta really is equals to omega divided by 2. Okay? Yeah. So we are really wrapping 这种卷啊，wrapping. We wrap the not wrapping. We pack the entire imaginary axis to a circle. I think it's a little interesting. Right? It's a little funny. Because imaginary axis is infinitely long, right? 它是一个无限长的一条直线啊。So this is a classic example of mapping an infinitely long line to a circle of finite length. To a circle of finite length. So that's kind of the important property of the bilinear transformation. It maps the infinitely long frequency range to the unit circle, which represents from -pi to pi. Okay. So 当然这个复数部分也是一样啊。So just similarly, when we consider negative big omega, then theta is also negative. So it maps the 0 to 0. Okay, it maps a zero frequency, map the DC to DC, and it maps infinity to Nyquist. Otherwise, in between, we have the arctangent relationship. Okay, so you can say that now we can finally plot small omega in terms of big omega. Okay, small omega in terms of big omega, we have it approaches plus pi as big omega approaches infinity. It's an arctangent function. 2 times arctangent function, it goes this way, and symmetrically in the negative for the negative part. This is an arctangent function when you express small omega in terms of big omega. Okay, so 我提前破梗了，这整段可以擦掉。I was trying to. Oh no, let me just leave it there. Let me just leave it there. What else? So that's one property we have found out that there's a explicitly. You can actually write down the explicit expression of how the imaginary axis, how this imaginary axis is mapped to the unit circle by writing omega equals 2 times arctangent, 然后呢 big omega 好像是这样。Yeah. Am I being correct? Yeah. That's an explicit expression for the mapping. Okay, this is explicit. Closed form. And secondly, I want to tell you, conformal mapping preserves contour orientation. What does that mean? That means when you go along a path, okay? Again, coming back to our kind of writing pad right here. Preservation of contour orientation. So that means if we have a closed contour, okay, in the S domain, and we go along it in the counterclockwise direction, okay? So after Z transform, not after Z, after the bilinear, should I say, doesn't matter which direction, okay? From one direction to the other, one domain to the other domain, it also maps to a contour. And what's counterclockwise in one domain remains counterclockwise in the other domain. That's what we mean preservation of contour orientation. 逆时针就逆时针，顺时针顺时针，不会变啊。因为变了就会不满足柯西黎曼方程，可能是这样啊。If you think about it 啊。And further, what's inside stays inside. So the inside, what's inside here, inside the contour, stays inside when we perform conformal mapping using an analytic function. Yeah? So why is this important to our life? 为什么知道这个人生需要知道这个？This time is important, because it means that when we perform this design by linear transformation, it maps the left-hand side of S-plane to the inside of the unit circle. What do we mean? So imagine that we are going along So maybe let me just keep writing right here, okay? So now, this is important to know because going along the imaginary axis in S, you can imagine this as a closed contour, even though it is not, okay? It's a contour of a circle with infinite radius. 这是长长的 trick. So imagine that this is a part of a circle which is infinitely large. 这样. A circle with infinite radius, okay? That's how we imagine it, okay? So if you imagine that, then going clockwise and counterclockwise means that the inside is on the left-hand side. Inside of this infinitely large circle, this disk, 这个盘子啊, its inside is left-hand side, right? But we have just told you that conformal mapping preserves orientation. So we can be sure that when we apply bilinear transformation to go to the Z domain, not only does the contour, the imaginary axis map to the unit circle, not only does the imaginary axis map to the unit circle, and we have just proved that, okay? Yeah. But the left-hand side remains on the left-hand side. The inside remains on the inside, okay? That's what it means for conformal mapping to preserve orientation. So now what happens? So now the inside or left-hand side of this contour is right here, right? The entire the left half plane, 左半平面, the left half plane now is mapped to the inside, to the left-hand side or the inside of the unit circle. It's mapped to the inside. Of course, you can also show this by other ways. But more generally, this is a property, a direct result from an intrinsic property of conformal mapping. Inside to inside, left-hand side to left-hand side, when you go along a path. So what does that mean? So that means that if your original analog system is stable with poles, I don't mean to use pencil. So that means that if your analog system originally has poles, is stable, so all the poles are located on the left-hand side. The zeros might be on the right-hand side, that's okay, yeah, but the poles are on the left-hand side, okay? When we have a stable analog prototype, after bilinear transformation, that it provides us with also an H of Z where all the poles are now mapped to the inside of the unit circle. Where poles are inside the unit circle, are inside the, inside, you know what I mean. You know what I mean inside the unit circle. Inside the unit circle. Left-hand side of S-plane is preserved, is moved to inside of unit circle after inverse bilinear transformation. Okay? So this is great because it guarantees us that if we begin with a stable system in analog, we end up having a system that's also stable, the digital system, through this way of design. Okay? Through this way of design. And that's why I said this is good to know. It's essentially a direct result from this nice property of conformal mapping in that the mapping preserves orientation of any contour. Okay, so enough about the properties of bilinear transformation. And here I put a note EE, EE is the meaning. Why is this meaningful to us? Because now we have stability preservation. Stability of the system is preserved. No need to worry about stability. You begin with a stable system, you design, after this design, you obtain a stable system in the digital world. And this is really nice, really nice to know. 好，那我想今天大概就主要就 cover 到这里主要 cover 到这里主要 cover 到这里。那我还是没有回答刚刚那个问题We got stuck here, right? Yeah. 埋一个梗好了So now when you go home, you are interested enough. Yeah. Now after knowing these properties, especially we know how big omega is mapped to small omega. Now can you plot, make a sketch of the frequency response as a function of small omega? And let me say that now the hint is frequency response is e to the j. Omega is a function of big omega, right? So that's a kind of insight. Okay, so try it at home. Right? Can you? If you're interested enough, please work out then how do we make a sketch of the magnitude response after this design, even though the system function may look scary. But please don't worry, it's pretty simple. Okay, after we understand small omega as a function of big omega. 大概就这样。Okay, so today I think I've talked about much of things I want to talk. Thanks again for being here and see you tomorrow.